Picture the Colorado River in the early 20th century. It wasn't the tame, regulated waterway we know today. It was a violent, unpredictable force that carved the Grand Canyon over millions of years, and it flooded the farmland of the American Southwest almost every spring with a fury that destroyed crops, homes, and lives. According to the US Bureau of Reclamation, the river's seasonal floods and droughts made the entire lower Colorado basin nearly impossible to farm reliably or to supply with drinking water. Something had to control it. The idea of building a dam in Black Canyon, on the border of Nevada and Arizona, had been floated for years, but the scale of what would be required was almost unthinkable. Engineers weren't just talking about a wall of concrete. They were talking about reshaping the flow of an entire river system, generating enough electricity to power a rapidly growing region, and doing it in one of the most remote, brutally hot stretches of desert in the country. Then the Great Depression hit. Unemployment soared, and the federal government needed a project that could put tens of thousands of people to work while solving a genuine infrastructure crisis. The Boulder Canyon Project Act, passed in 1928, authorized the dam's construction. 6 construction companies banded together under the name 6 Companies, Inc., to win the contract. What they were promising to build, in a place with no roads, no town, and no easy water source, was a structure that would become the tallest dam in the world at the time. Before a single bucket of concrete could be poured, though, engineers faced an immediate and violent obstacle. The river itself was still flowing directly through the canyon where the dam needed to stand. You cannot build a dam in a river that's actively flowing through the canyon. So the first true engineering challenge at Black Canyon wasn't the dam at all. It was moving the Colorado River out of the way, temporarily, without stopping it completely. The Bureau of Reclamation's own records describe how crews drove 4 massive diversion tunnels through the canyon walls, 2 on the Nevada side and 2 on the Arizona side, blasted through solid rock. These tunnels were built to reroute the entire flow of the river around the future dam site, while construction proceeded on dry riverbed. Think about the audacity of that plan for a moment. Workers had to tunnel through a canyon wall, under desert heat, while the river that had carved that very canyon over geologic time kept flowing just feet away. Once the tunnels were complete, crews built cofferdams, temporary barriers upstream and downstream of the construction site, to hold back the river and funnel it into the diversion tunnels instead of through the work zone. This let engineers pump out the riverbed and begin excavating down to bedrock, which is essential for a structure that needs to anchor itself against the canyon walls rather than simply sit on loose sediment. After the dam was completed, some of these diversion tunnels were repurposed as part of the spillway and outlet work system, so the infrastructure built to get the river out of the way became permanent parts of how the finished dam manages water flow. This diversion phase alone took years of grueling labor in extreme desert conditions before construction on the dam's actual concrete structure could even begin, and it set the stage for the project's defining technical puzzle. How do you pour that much concrete without it destroying itself from within? Here's a problem most people never think about. Concrete generates heat as it cures. That's not a minor detail, it's chemistry. The hydration reaction that hardens concrete is exothermic, and in a structure of Hoover Dam's scale, that heat becomes a serious threat. The Bureau of Reclamation states that the dam contains roughly 3.25 million cubic yards of concrete. If engineers had attempted to pour that volume in one continuous mass, the interior would have taken an extraordinarily long time to cool, and as it cooled unevenly, the concrete would have cracked under the internal stress. A dam riddled with cracks isn't a dam you can trust to hold back a reservoir. So the engineering team devised a solution. Instead of one monolithic pour, they poured the dam in a network of interlocking rectangular columns, essentially building it up like enormous concrete blocks, stacked and keyed together, each poured in relatively shallow lifts so the heat could dissipate before the next layer went on. To speed up the cooling even further, Engineers embedded a network of steel pipes throughout the concrete structure and circulated cold river water, and later refrigerated water, through them to actively pull heat out of the curing mass. Once each section had cooled sufficiently, the pipes were filled with grout and left permanently embedded in the structure. This cooling system meant the concrete could cure safely in a fraction of the time it would otherwise have taken, which mattered enormously for a project racing against the Depression-era imperative to deliver results and jobs. It's one of the clearest examples in the entire project of engineers identifying a problem invisible to the public, the literal thermodynamics of curing concrete, and solving it with a purpose-built system embedded permanently inside the structure. None of this happened without an enormous human workforce living in brutal conditions. Thousands of workers converged on the site during the Depression, desperate for jobs, and the federal government built Boulder City, Nevada specifically to house them, since there was no existing town anywhere near Black Canyon capable of supporting a project this size. Summer temperatures in Black Canyon routinely soared into dangerous territory, and the work itself was hazardous by nature, involving explosives, heavy machinery, and, most dramatically, the men known as high scalers. These were workers lowered by ropes down the canyon walls to remove loose rock before construction, dangling hundreds of feet above the riverbed, often with only their skill and their harnesses standing between them and a fatal fall. The US Bureau of Reclamation's official record documents 96 industrial fatalities during the construction of the dam. That's a sobering number on its own, and it reflects just how dangerous this project truly was, without needing any exaggeration. And that's important, because there's a persistent myth about Hoover Dam that needs to be addressed directly. The story that workers who died during construction were buried inside the concrete itself, entombed in the structure. The Bureau of Reclamation explicitly and directly debunks this claim. It is not true. The pours were done in shallow, carefully monitored lifts, specifically so the concrete could cure properly, which also means there was no scenario where a body could simply vanish into a pour undetected. The myth likely persists because it's a dramatic, almost mythic image, a monument literally containing the sacrifice of the men who built it. But the real history, 96 confirmed fatalities among a massive workforce doing genuinely hazardous industrial labor, is sobering enough without inventing something that never happened. So why does Hoover Dam look the way it does, that distinctive curved wall bulging toward the water it holds back? This is the arch-gravity design, and it's a piece of structural engineering that does double duty. A pure gravity dam relies entirely on its own weight to resist the pressure of the water behind it, which means it has to be enormously thick and heavy. A pure arch dam, on the other hand, transfers the water's pressure sideways into the canyon walls, the way a stone archway transfers weight down into its supporting columns, which lets it be much thinner. Hoover Dam combines both principles. Its curved shape pushes a significant portion of the reservoir's force outward into the solid rock walls of Black Canyon, while its sheer mass, that 3.25 million cubic yards of concrete, still provides gravitational resistance as well. According to the Bureau of Reclamation, the dam stands 726.4 feet high, which made it the tallest dam in the world upon its completion. This hybrid design was essential because Black Canyon's rock walls were strong enough to bear substantial lateral load, allowing engineers to build a structure that was both shorter in base thickness than a pure gravity design would require, while still safely holding back the millions of acre-feet of water that would eventually form Lake Mead behind it. It's worth pausing on the sheer confidence this required. Engineers in the early 1930s did not have modern computer modeling. They relied on physical testing, slide rule calculations, and a deep understanding of material science and structural mechanics to design a structure that has now stood for roughly 9 decades without failure. The completed dam, remarkably, was finished in 1935, according to the Bureau of Reclamation, 2 years ahead of its original schedule, an outcome almost unheard of for a project of this magnitude and difficulty. Hoover Dam wasn't built as a monument. It was built to do a job, and it's still doing that job today. The dam's power plant houses hydroelectric generators that convert the force of water dropping through the structure into electricity, which is distributed to utilities across Nevada, Arizona, and California. This was, and remains, one of the largest hydroelectric facilities associated with a single dam structure in the United States, and its output has served as a foundational piece of electrical infrastructure for the Southwest for generations. Beyond electricity, the dam's other core purpose, water management, continues to shape the entire region. The reservoir it created, Lake Mead, is the largest reservoir by volume in the United States when full, according to National Park Service records, and it supplies water for irrigation and municipal use across multiple states and into Mexico. That original problem the engineers set out to solve, an unpredictable river that flooded in wet years and left farmland parched in dry ones, was fundamentally reshaped by this single structure. Water, that once rushed downstream in an uncontrolled seasonal torrent, is now stored, measured, and released according to planned allocations that support agriculture, drinking water systems, and cities that did not exist at the scale they do today when the dam was built. It's a striking thing to consider. A structure conceived and built during the depths of the Great Depression, using 1930s-era engineering tools and techniques, remains a load-bearing piece of infrastructure for tens of millions of people across the American Southwest nearly a century later. Few infrastructure projects from that era can claim that level of continued relevance. What makes Hoover Dam endure in the public imagination isn't just its scale, it's the combination of desperate circumstance and audacious problem-solving that built it. This was a project conceived to fix a genuine crisis, an unpredictable river threatening the water and power future of an entire region, and executed by a workforce that took on the job during the worst economic collapse in American history. The engineers had to solve problems that had never been solved at this scale before. Diverting a major river through tunnels blasted into solid rock, managing the literal thermodynamics of curing millions of cubic yards of concrete so it wouldn't crack itself apart, and designing a hybrid arch-gravity structure that could stand up to immense hydraulic pressure using the engineering knowledge available in the early 1930s. And it came at a real human cost, the 96 lives lost during construction, according to the Bureau of Reclamation's own record, a fact that deserves to be remembered honestly rather than mythologized into something it wasn't. What stands in Black Canyon today, still generating power and still holding back Lake Mead, is proof that some of the most consequential infrastructure in American history was built not with modern computing power or advanced material science, but with rigorous engineering fundamentals, relentless labor, and a willingness to solve problems nobody had solved before. That's really the through line of every mega project we cover on this channel. The gap between an impossible-sounding problem and a functioning solution is closed by people willing to work through it piece by piece. If you want to keep exploring how humanity's biggest engineering achievements actually got built, subscribe to MegaBuilt, and we'll see you in the next one.